Likes examples of times when you might use rice boxes. The practice that was on the rice box notes, I would say those are some good introduction to using rice boxes questions. And you want to be able to do those. And you also want to be able to do some questions that I think are a little bit more sophisticated, involve a little bit more math, a little bit more nuance. All right, so we'll go through questions 1 to 6 here. So I'm going to highlight the key ideas here. All right, so okay, so we got for number 1, a reaction mixture is at equilibrium. Okay, so that's a good thing to note here, is at equilibrium. And it contains a mole of hydrogen gas. Okay, that's important. 2 moles of carbon dioxide gas. 2 moles of carbon monoxide, and then another 2 moles of water. And that's in a 2-liter bulb. So maybe I'll just highlight the 2 liters separately. 2-liter bulb. Okay. And that's living at equilibrium. All right. Then a 1 mole of hydrogen gas is added to the system. Okay. And then the question asks us to calculate the carbon monoxide concentration, which will exist after equilibrium is, okay, so equilibrium is reestablished. We want to calculate the carbon monoxide concentration. Okay, well, this looks a lot like example 4 that we went over on Monday afternoon. And by afternoon, I mean morning. So that means it looks like we have, for our reaction, we know the concentration of hydrogen. We have a 1 mole for 2 liters. Sorry, pardon me, 1 mole for 2 liters. We know the concentration of carbon dioxide gas, carbon monoxide, and hydrogen, which I think would allow us to find the equilibrium constant. So, I mean, let's find it. All right, so the equilibrium constant, KEQ, will be the concentration of our products over our reactants. And it looks like the coefficients on each of these are 1, and so don't have to worry too much about powers. All right, and so what do we have here? Concentration of carbon dioxide, 2 moles for 2 liters. Okay, so that's 1 mole per liter. Hydrogen is 1 mole for every 2 liters. And then we have carbon monoxide, which is 2 moles for 2 liters. 2 for 2 is 1. And 2 moles of hydrogen, or sorry, pardon me, H2O or water for every 2 liters. So that's another 1. All right, so that means our KEQ is equal to 0.5. I'll keep another couple sig figs, I guess, because of so many sig figs I have in my values. Okay. My KEQ is 0.500. All right. Well, maybe that'll come in handy. So now we're going to disturb equilibrium. We're going to add more hydrogen gas. As a result, we should expect equilibrium to shift to the left. Okay, so that's what we're going to look at here. And once that happens, and this tries to reestablish itself, what's the concentration of carbon monoxide when we're done? All right, well, let's find out. So this sounds like we're going to need a rice table. We have initial conditions here, and then we're going to be looking at an equilibrium. We're going to be comparing across from initial to equilibrium. Those are the I and E in ice tables, or pardon me, rice boxes. All right. So we'll start with a nice rice box. I'll write the reaction out. So we've got some carbon monoxide. I'm going to skip listing the phases because the phases are all gaseous. And our initial values, well, this is really important here, are going to, well, our initial concentration of carbon monoxide is going to be 1.5 1.00 moles for every liter, because it's 2 moles for 2 liters. And of course, we only talk in concentration here. Then we have the water, which again is 1.00 concentration. The carbon dioxide, again, is 1.00. Now, for the hydrogen, we start with 1 mole, and then we add 1 mole more. And that starts this new situation where we have to readapt to equilibrium. So we have this 1.00 moles plus 1.00 moles. But of course, that's divided by 2.00 liters, which of course equals 2 over 2, which is 1.00. All right, and so what do we know? We know that this is going to shift to the left because we're increasing hydrogen gas, and to decrease it, to adjust so that we keep this constant the same. That means we're going to subtract some amount of hydrogen gas, and the same amount of carbon dioxide has to be consumed as a result. That means we're going to, as a 1-to-1 ratio of water and hydrogen, means we're going to add, X, and we're going to add X moles of carbon monoxide. So our equilibrium should be 1.00 plus X, 1.00 plus X, 1.00 minus X, 1.00 take away X. Okay, now we just have to solve for our variable X. So our equilibrium constant is going to be our concentration of carbon dioxide and hydrogen. 1.00 minus X, 1.00 take away X, concentration. Oh, I guess I don't need regular parentheses because I'm actually just putting in my concentration values. 1.00 plus X, which you may notice is 1.00 take away X squared over 1.00 plus X squared. And I know my KEQ value. I found it earlier. And we know that our equilibrium constants can only change if you change the temperature. If you change the concentration, well, the ratio of product to reactants is just going to readjust, which is what it's doing right now, to reduce that change and keep our constant the same. All right. Now, in order to undo these squaring, so, I mean, if we expand these binomials by, like, rewriting as 1 minus x times 1 minus x and then foiling it out, we're going to get a big mess, and we're going to have to solve a quadratic equation. So in order to prevent that occurring, we're just going to square root both sides like this. All right, and so square root of a half is 1 over root 2. Okay, whatever. All right, so that gives us 1.00 take away x over 1.00 plus x, and that's equal to the square root of 0.5, which I think is 0.707. Where did my calculators go? 0.5, yeah, 0.707. 0.707. All right, so now we need some grade 11 level solving of rational expressions. And so we got to multiply by the denominator here in order to get rid of it. And we'll do that on both sides. 1.00 plus x times 0.707. These guys cancel because we're dividing and multiplying by the same thing, undoing the division by doing the opposite. And then we distribute a 0.707 to both of these terms. So 1 times 0.707 is 0.707 plus 0.707x. And now I need to group all the x's on one side and all the terms without x's on the other. So I'm going to add x to both sides, which is, of course, adding 1x. I'm going to take away 0.707 on both sides as well. And things are getting a little hairy, so I'm going to cross these guys out to indicate and simplify for myself. All right, that looks like I get 1.707x on the left And, ooh, 0.2, I don't know. It's too late in the day for that, so 1 minus answer, 0.29, okay. 0.293, I'll round that to. Okay, and then lastly, I'll divide by 1.707 to isolate x. And it gives us a value of 0.172. 0.172 watts. Well, what did x even represent? Let's go back to our original question. What did our unknown measure? Well, it looks like it measured the change in concentration, the reduction in concentration of our products, and the increase of the concentration of our reactants. So that means it's a concentration, so it's measured in moles per liter, or molar. Now, we should probably label that. That is the change in concentration of our products and reactants. I don't remember what the good abbreviation for reactants is. Well, whatever. Now, that is not what we were asked for. We were not asked how much did the products and reactants change. If we look back at our question, we're asking to calculate the carbon monoxide concentration, which exists when equilibrium is reestablished. So if we look, we see our carbon monoxide concentration after equilibrium is reestablished is 1 plus our value for x. So our concentration of carbon monoxide at equilibrium is going to be 1.00 plus x, which is 1.00 plus 0.172, which is 1.172, which if we want to conserve our sig figs, it means that our concentration of carbon monoxide at equilibrium is 1.17 molar. And that's us done. So we will move on to question 2. Let's get a nice yellow page here. All right. So question 2 says, okay, we've got a KQ of 7.5. Okay, that sounds important. All right, and we've got a certain amount, which means an unknown amount of hydrogen sulfide. That's not quite the name of that, is it? A certain amount. That makes me think variable. An unknown amount. Okay, but who knows? So let's finish reading the question, and we'll decide what our variables are going to be. A certain amount was added to a 2-liter flask. Okay, that also sounds important. 2-liter flask. And it was allowed to come to equilibrium. So we reached equilibrium, and that always seems to be important to know when we're at equilibrium and when we're not. At equilibrium, 0.072 moles of hydrogen gas were found. At equilibrium, how many moles of hydrogen sulfide were originally added? Okay, so, I should probably highlight the question. So how many moles of hydrogen sulfide were originally added? All right, so let's move on here. We got question 2. It says, looks like we are comparing an initial amount, which is what we're asking for, how many were originally added. That means initial. And this means at equilibrium, so that's an equilibrium value. All right, so we're comparing initial conditions to equilibrium conditions. So that sounds like rice table material. So let's move right on to write out a rice table. All right, so our reaction is we have 2 H2s plus some sulfurs. And I didn't know sulfur comes in a diatomic gas like that. Does it? I need to think about that. All right. So what are our initial situations here? Well, it looks like all we were adding to this initial flask, that was 2 liters, was some amount of hydrogen sulfide. Okay. So that means I know that I have no hydrogen or sulfur in my original equilibrium flask. Pardon me, my original flask. Okay. I have some amount here. And I have a choice at this point. I could put my variable here, x. Maybe I'll do that. I'll just put x here. I guess what I was toying with is the idea that if I know that I'm looking for the number of moles rather than the concentration, I could say x over 2 if I wanted to, because I know my volume is 2.0 liters. But I think I'll just break it into 2 steps. I'll find x, and then I'll go back to the original question and answer a question about moles. But I know x. I'll just find it. X is concentration H2S initially. I think I'll get in the habit of making a note about that. All right. And then what do we know? We know at equilibrium we have some hydrogen gas. So that means that guy lives here, 0.072. And that's it. All right, so that means we should be able to answer all the rest of these questions. So we should be able to say, okay, I can figure out the change. Change is 0.072 moles per liter. Oh, oops, moles. This is a concentration. This should be in moles per liter. So that's 0.72. I'll make a note about that. So my concentration of hydrogen at equilibrium should be 0.072 moles over 2.0 liters, which is 0.036, capital M. So can I do this without making it too messy? Maybe I can. Look at that. Nobody will be the wiser. Okay. Okay, so if I add this much sulfur, I must have added half as much. Pardon me, if I added this much hydrogen, I must have added half as much sulfur, because of the ratio for every 2 moles of hydrogen that are produced, only 1 mole, or half of that many moles, of sulfur are produced. So I'm going to divide this value by 2, and I get to add 0.018 moles. That gives us a total value, 0.018. And then I can ask how many moles did I lose? Well, it must have been, this is a 2-to-2 ratio of hydrogen to hydrogen sulfide. So that means I can subtract 0.036 moles for every liter. All right, so the equilibrium concentration is going to be X, take away 0.036. All right. Our rice table is finished. Now is a good time to move to an equilibrium expression. Which is going to be our H2S squared over our hydrogen concentration squared times our sulfur concentration, which is X minus 0.036 squared over 0.036 squared over 0.018. And that's all equal to our equilibrium constant, which is 7.5. That's equal to 7.5. All right, and now we just need to solve for x. This looks actually like not so bad a math problem. I'm going to start by multiplying the denominators together. 0.036 to the power of 2 times 0.018. Okay, so it's pretty small. So x minus 0.036 squared over 0.0000233. That's all equal to 7.5. So to get rid of my denominators, I'll multiply by them on both sides. So 0.000233 times 0.0000233. So multiply that all by 7.5. Okay, so that cancels out on the left. So I get just x minus 0.036 all squared. That's equal to 0.000175. I'll square root both sides to undo this square. If I was in math class, I would have to worry about plus and minuses, but in chemistry, we don't have to worry about that so much. And that's equal to whatever the square root of this is, which is 0.0132. And then I can add 0.036 to both sides. And I want to add 0.036. I find my x value is 0.0492, and what was the x even measuring? It was measuring the concentration of hydrogen sulfide in my initial conditions, so I'm going to give that a units of moles per liter. Now, that's the concentration, but the question asked how many moles were there? And this says how many moles there are for a liter, right? That's what this means. It means 0.0492 moles for every 1 liter. And I've got 2 liters, so I must have twice of this many. But to clarify that, first I'll say, make a note, this is the concentration of H2S initially. And then to find the number of moles, I'm going to multiply by the volume. Moles of H2S for every 1 liter times 2.0 liters. And that's going to go for 1, cancel out liters. And it turns out I multiply by 2, and I can see why now, so I'll just times it by 2. And I get 0.0985 moles of H2S. All right, let's move on. Question 3 says we've got a reaction at equilibrium, so it's at equilibrium. Okay. And then it has some quantities of carbon dioxide, 4 moles it turns out, 1.5 moles of hydrogen gas, 3 moles of carbon monoxide, 2.5 moles of water, and this is all in a 5-liter container. Okay, so that sounds like we have moles and the volume of each of the substances, so we should be able to find a KEQ. Question mark. So that's just a little thought. All right, and the next question, or pardon me, the rest of the question says, how many moles of carbon dioxide? Okay, that sounds like, how many moles of carbon dioxide would need to be removed in order to reduce the amount of carbon monoxide to 2.50 moles? Well, that's an interesting question. Okay. So let's read through that again slowly here. So it sounds like we're going to remove carbon dioxide. So we're going to remove carbon dioxide and decreasing its concentration. Okay, so what's that going to do? That means equilibrium is going to shift to the left, to the reactant side, to try to establish equilibrium and increase the amount of carbon dioxide and hydrogen gas, decreasing the amount of carbon monoxide. So we want to remove enough, a sufficient amount, to decrease this to 2.50 moles, starting at 3.0 moles. I wonder, maybe I can use the same color here. Maybe I'll use pink to underline these two values, which are both about carbon monoxide. So we want to reduce the amount of carbon monoxide to 2.50 moles. And the only thing it seems like we can manipulate in the system to do that is carbon dioxide gas. We're going to remove as much as possible until we get to this amount. Okay. It's okay to not know exactly where to go with a question. But, I mean, if that's the case, we should really just do anything we can. I mean, to be honest, I don't know exactly how this question is going to work, but I have confidence that if I just start by doing anything that sounds reasonable, I can find my way to an answer. So I mentioned earlier that we have enough information to find the equilibrium constant for this reaction. So maybe we should start there. Our equilibrium constant is going to be our concentration of carbon monoxide times our concentration of water divided by our concentration of carbon dioxide times the concentration of hydrogen gas. Okay, and what's our concentration of, let's start here, carbon monoxide. That's 3 moles for every 5 liters. I'm going to write that in. 5.0 liters. All right. Water, how much water do we have? We have 2.5 moles for every 5.0 liters. And how much carbon dioxide do we have? We have 4 moles for every 5 liters. And then I have some hydrogen. How much hydrogen do I have? I have 1.5 moles for every 5.0 liters. All right, these work out to pretty nice numbers. That gives me 0.6 over 0.5, 0.8, 0.3, which is to say we get 0.3 over 0.24, which is the same thing as saying 30 over 24, which I think is enough to work and get into a calculator. So that gives us our KEQ, which is 1.25. All right. So that wasn't what we were asked, but okay, now we found a KEQ. Maybe that'll come in handy later. Maybe not. All right, so what do we have now? We're going to remove some carbon monoxide. Pardon me. Looks like we're going to remove some carbon dioxide so that we reduce the carbon monoxide to a new equilibrium concentration. Sounds like we're starting with initial concentration, and we have this final concentration after a change that reestablishes equilibrium. So I think there are some ways in which it's going to be similar to question 1. So I think maybe I'll start putting this in a rice table and see how much I can fill out here. All right, so the reaction is carbon dioxide plus hydrogen gas. It lives in equilibrium with carbon monoxide and water. All right. And what do we know? So I'm going to come back to carbon dioxide. Let's move on to hydrogen. We know initially, before we remove anything here, or when we remove something, we'll still have 1.5 moles of hydrogen for every 5 liters. Hydrogen, 1.5 moles for every 5 liters. That gives us a concentration of, as we found before, 0.30 molar. Carbon monoxide, 3 for every 5 liters. That gives us a concentration of 0.60. Water is 2.5 moles for every 5 liters, which is 0.50 moles per liter. And I know how much I'm going to start with. So I guess I have two choices. I'm going to choose a variable. So I think that's what I'll do. I'll just say x. X equals the concentration of carbon dioxide initially. Okay. You know, I could have said my concentration of carbon dioxide is 4 takeaway x divided by 5. But I think that might have been a little messy, and I don't know how that's going to fit into, maybe I'll have an equilibrium concentration. I'll need to put that whole fraction into it. It might make it be a little hairy, so I think I'm going to just keep it a little simple here. All right. And lastly, what do I know? I know that ideally this system will reestablish equilibrium with the carbon monoxide at 2.5 moles for every 5 liters. So my carbon monoxide is now going to adjust, so it's going to be 2.5 moles for every 5 liters, which is 0.50. All right, so that shows me how much we're going to lose. So, or we're going to reduce by 0.10 moles for every liter. And for every amount of carbon monoxide I'm going to lose, we're going to lose that much water. Which gives us 0.40, and then we're going to add that much hydrogen and add that much carbon dioxide because that's what's going to get us carbon monoxide. Okay. So that means I'll have a concentration of 0.x plus 0.1 and 0.40. Okay, so that looks like I have all my equilibrium concentrations in one variable, so I should be able to put that into an equilibrium constant expression. So my KQ is going to be equal to my products over my concentration of my reactants. And so I know my KQ value, which I found earlier, is 1.25. And it's going to be equal to, my products are going to be 0.50, 0.40. I guess I only need regular parentheses because these are our concentrations. I don't need to indicate that they are. X plus 0.10 times 0.40. Well, these 0.40s cancel out, so that's nice and easy. I've got a variable in the denominator, so I need to multiply both sides by that expression. I shouldn't use it x for multiplication because x is my variable. So I'm going to multiply both sides by x plus 0.10. That's going to get distributed inside the distributive principle. 1.25x plus 0.1, so 0.1 of 1.25 is 0.125, and that's equal to, well, these guys are going to cancel out too. So I get 0.50 left. Well, that's actually a pretty easy expression. Grade 9 could solve this one at this point. So if you have a brother or sister in grade 9, you can go ahead and ask them to solve it for you and go get a sandwich. So we get 0.375, 1.25x. Okay, and then I'll just divide both sides by 1 1/4. Alright, and then we get this divided by 1.25. And I get x is 0.3. Alright, now what was x? X was the concentration of carbon dioxide initially, right? Okay, so that means this is measured in molar, which is the concentration of CO2 initially. Okay, and the question was, how many moles of carbon dioxide would need to be removed from the system in order to reduce the amount of carbon monoxide to this amount. Okay, so we know that now the concentration that you would need to have in order to induce this change. So the question is, if we had 4 moles to start with, well, that tells me that if this number, when we turn it into moles, isn't smaller than 4.0, then that means we made a mistake somewhere. All right, let's find out then. Okay, so if I have 0.30 moles of CO2 for every 1 liter, and I have 5 liters, now liters should cancel out, and I should get 1.50 moles. Interesting. So this is the amount of CO2 I would want after removing CO2 in order to push equilibrium to reduce the carbon monoxide concentration to 2.50 molar. But that wasn't the question either. We were asked how much would we have to remove, not how much would we have after removing. So I'm going to start with my 4.00 moles. So okay, so if I have my 4.00 moles CO2, I'm going to remove X moles. Maybe I shouldn't use X, I just used X. Let's say Y. Big fat Y. So letter Y, nice and neat. Of CO2 is going to leave us with 1.50 moles CO2. Okay, so I could isolate Y using algebra, but I can see that that number is going to be 2.5. 4 take away 2.5 gives us 1.5, right? So that means we would need to remove 2.50 moles of CO2. That's the question. Okay, so I think I'll pause there and I'll start the rest of the questions on a new video. Ask me if you have any questions about these guys. That one was, I would say, a pretty spicy question. There's a lot going on there.